share screen. Okay. All right. Welcome to CE 526. In today's lecture, we are going to talk about observational before and after studies. And I hope you are all can see my screen here. Okay. If you're not able to see the screen, please raise your hand. But if you are, then everything is good. You don't have to worry about anything. If you're not able to see the screen, let me know. Okay, perfect. Okay, so I'm going to hide the meeting controls. So today's lecture, we are talking about observational before and after studies. And the observational before and after studies are very critical, very, very important piece of safety analysis because, and in some ways, they're also very critical to how we make decisions. So ultimately, it's a decision making. It's very, very important, very critical for decision making, and because it's so important to safety. And what we are trying to do with this approach, with the observational before and after studies, is that we are trying to figure out if we did a safety intervention at a location, like for example, we replaced a two-way stop control intersection with a roundabout, or we replaced a signalized intersection or unsignalized intersection and converted into a signalized intersection. Did that improvement really work for us? That's really the question we're asking ourselves with the observational before and after studies, is that the improvement that we made on a roadway location, did that work for us? So here is sort of the problem that we are trying to solve with this. To assess whether a crash countermeasure worked or not, right? So what you need to estimate is what would be expected to happen in the future if no action were taken, right? So first things first, and I'm sure some of you at least have done the reading assignment, so hope it's not completely foreign to you, and you'll prove it to me by taking a little quiz on it a little bit later in the class today. But first, let's talk about some things that are of interest here. I'm calling this the observational before and after study. So what does it mean? What does the term observational mean here? And I want you to think about observational as opposed to experimental. So experimental study versus an observational study. So maybe some of you, like if you're keeping up with the news, maybe you guys would know about what's an experimental study. Does experimental study ring a bell to you? What do you think? So I'm kind of going away from observational for a little bit so that I can contrast it and explain it to you. But let's first start with the idea of an experimental study. What does it mean to do an experimental study? So if you maybe quickly want to raise your hand or type in the chat box, what do we mean by experimental study? If you want to just say it by voice, then raise your hand. Otherwise, feel free to type. What does it mean when you hear the term experimental study? So I have something in the chat. You have a control to compare to. Okay, thank you, Simon. So Simon says, that's a game, right? Simon says, anyway, so Simon types up in the chat box is that you have some control to compare it to. But in observational study also we could have control, so that's not, but I know what you're getting at, so you're on the right track, but it's not quite the precision I'm looking for. So any other thoughts on what's an experimental study? Right? Trying to prove or disprove a hypothesis. Yes, that's the purpose of the experimental study. That's completely correct. William has a thought on identifying the road the treatment could work, place the treatment, and seeing how it affects the crashes. Um, I will let it slide that, and I'm not even going to name the student now. Somebody type accidents on the chat box. I don't like that. Let's call them crashes. And I know the tutorial, because it's such an old document now, back from 2000, from ancient times, that still uses the term accident. So my apologies for providing that resource to you, but it's still a very valuable resource. But let's not use the term accident in this class, okay? So William, what you have suggested about identifying a treatment and placing it and how it affects the crashes, that might actually be an example of, like, what you have to do that. You might need an observational study and not necessarily an experimental study. Okay, so I'm going to try to at least get at that. I don't see any raised hand on there, so nobody wants to actually talk, which is fine. Now, so let me talk a little bit about experimental studies. So listen up here, if you sort of wandered off a little bit. So experimental study are studies where you are trying to figure out or test an hypothesis in a very controlled environment, where you are interested in something. Your hypothesis is very specific, and you are interested in finding out what is the impact of a particular intervention, and you are able to control everything else, right? So a good design of experiment application is your randomized control trials that you see, and that's what I was meaning to get at when I said the idea of what if you've been following the news, and that's the news of the vaccine, right? So you judge the effectiveness of the vaccine, or you try to assess the vaccine in a randomized controlled experiment, RCE trials. And what happens there is that they will control for everything. They would want to make sure that the population that they are selecting at random, and then at random they will select a large sample size of random population, and then they will give some of those patients the actual vaccine, and then some of the other ones, some of the random population will get the placebo. Basically, there is no drug; it's just no substance really to that. And then they look at, okay, incidences of disease and how that differs, and they are trying to control for everything. So our drug trials are essentially experimental studies, because they do want to control everything. They need to control everything except for the fact that who gets so the only difference between the trial population is that some of them will get the placebo, some of them will get the vaccine, and then the sample would be large enough so that the only difference between the set of populations is that they are only differing in the aggregate. Their only difference is that one of them gets the vaccine, one of them gets the placebo. One group gets the vaccine, one group gets the placebo. Okay. In traffic safety, however, we don't have that luxury. We cannot control everything. When we do interventions in traffic safety, we are not going to be able to control who uses the intersection. We're not going to be able to control who uses other intersections in the neighborhood. We are not even going to be able to control how much traffic now uses our facilities. And so observational and experimental. So observational study is where you don't have a lot of control, but you try to figure out some statistical methods in which you try to get closer to a quasi-experimental design. You're never going to be able to achieve an experimental design that you might be able to get in the lab setting. And everything is a scale, by the way. It's not like a dichotomy where something is experimental versus something is, so it's not a step function of experimental versus observational. What it really is a sliding scale, and our traffic safety studies will be on the observational end, And the vaccine trial will be somewhat on the experiment, or going to be mostly on the experimental end. And then obviously the experiments that you might have done in your chemistry lab, right? With pipette tubes and titrations and all that, those are very, very controlled experiments, right? So they are, controlled experiments. So it's all a sliding scale. And in observational study, you're sort of moving to a place where you don't have much control over anything, but you still try to find some statistical methods where, and then you try to figure out, okay, what kind of study you're doing. Okay? And then our studies are obviously going to be observational. And then you could run observational studies as a before and after, and you can run it as a cross-section study, right? So observational study, in before and after study, we are going to talk about that. So empirical Bayes method is a method to do that, observational before and after study. And then cross-sectional studies are basically studies when you're not so much interested in before and after the intervention. You are basically collecting a large sample size of roadway locations, and then you're trying to model the safety outcomes at those locations. And then based on that cross-sectional data analysis, you're trying to figure out, okay, what's the impact of doing something at a location, right? So basically you will collect data from, in a cross-sectional study, you will collect data from 300, 400, 500 different roundabouts. And then you'll try to have traffic volume as one of the variables in the mix. And then based on that, you can figure out, okay, what's the impact of traffic volume on safety of a roundabout? Or it could be configuration of the roundabout. Or it could be, the approach speed limit at the roundabout. So in a cross-sectional study, you try to collect data from hundreds of roundabouts, and then you try to model it using some statistical model. Maybe it could be a crash frequency model, like the one you will develop later in this class. And then based on that cross-sectional study, you just figure out, okay, what's the impact of a certain design parameter on safety, on number of crashes, right? But in here, what we are trying to do is before and after study, where we'll select the intervention, and then using a before and after design, we'll try to figure out what's the impact of that intervention on safety. Okay. So I'm just going to go ahead and write down the problem. So agency plans next year to implement a crash countermeasure that will reduce the crashes by 35% over the next 3 years. You need to estimate the benefits of this countermeasure. How do you go about doing that? Okay, so our before and after study is designed to solve this exact problem. How do you estimate the benefit of a particular countermeasure? So let's say an agency implemented an improvement. They were expecting 35% crash reduction. And let's say once they implemented it, did they actually achieve it? That's the question you're trying to answer. Okay, so that's the context of this lecture. And with that, I'm going to take a little pause here. And I'm going to go ahead and stop sharing as well. And what I would recommend now for you to do is that I'm going to open up the quiz in the next couple of minutes. And you might want to open up that tutorial that based your reading assignment on. It's just 2.5 pages. So I'll go ahead and open that. And in the meantime, I will just basically open that quiz. And what I want you to do is like that you will have 4 questions total. And everybody will get slightly different set of questions from the quiz. And in those 10 minutes, I haven't yet opened the quiz, but I'm going to go ahead and open that. But in those 10 minutes, go ahead and take the quiz. I've set the stage for you a little bit, but that's really independent of your reading assignment. So if you did the reading, you probably saw new information in what I've talked about so far, but it just should help you sort of set the context. So what I'll do now is I'm going to take a brief pause here, and I'm going to ask you to open up that reading assignment. And hopefully some of you have already done the reading, and go ahead and open that and be ready to take the quiz. And I am going to pause the recording. And in the meantime, just please go ahead and prepare to take the quiz. I'll open up the quiz in the next minute or so. Okay. Thank you very much for taking that quiz. It was a simple quiz, and I know it probably did not require 10 minutes. But again, this is just a simple reading assignment-based quiz. So my goal obviously is to have you read this before, but then also if you haven't read this, at least get some semblance of what this is talking about. So at least give you about 10 minutes to read through that material so that you're prepared for the lecture. So don't worry about too much about the score. I know most of you did very well. Like some of you got one question wrong, which is fine. And it looks like one of the questions where there was most people, or at least higher number got wrong, was the question on the precision of the estimate. So let's talk about that in just a minute as we proceed with the lecture. So what I'm going to do now is I'm going to get started with continue with the lecture on observational before and after study, and then when we get to the point where each of those questions sort of come up, I will just try to answer those questions, from the quiz, and make sure that everybody understands what we're trying to get at with each of those statements. Okay. I'm going to go ahead and share my screen again. So the problem is, if you are going to implement a crash countermeasure and you want to see what the benefit are going to be, so a common approach is to use 3 years worth of crash data. Okay, so I show here 2008, 9, and 10. 2008 had 30 crashes at a location, then 19 crashes, and then 21 crashes. So you can see that there is some variation in the numbers themselves, even within 3 years, that crashes have been as low as 19, but then also have been as low as much as 30, as many as 30. So you can average the numbers out, and 3 years will give you some idea about what is the expected crash frequency at that location. Okay. Then you could go further back in time. You could go as far back as 10 years, or whatever number of years you would like. So you could see the number. And then you could see that some of the years really have really low number of crashes, right? And this is just a hypothetical example, but if you were to look at real data, as you would in TIMS, if you were to do that, or any real crash data set, really, you would expect that there would be different numbers of crashes that occur every year. And the number can vary widely. You can see if you go back 10 years, 2005 had only 9 crashes, and then 2008 has as many as 30 crashes. And again, you can average them out to get an estimate of the expected number. So that's one way of doing the expected number. And then you can compare that expected number to what you observe after the intervention. And then you could see that then that can get you a potential answer for what kind of improvement did you actually achieve. Okay. Now, obviously, there are some challenges I think that we've talked about going back too far in time, because there could be, maybe design changes at a location. Maybe 2005 was maybe this data comes from, maybe city of New Orleans or something, where, in 2005 there was like a population drop, and not as many trips being made. And then obviously 2020 data could be interesting, is that maybe the overall crashes went down, but the fatal crashes went up, so on and so forth. So there could be many reasons for the crash patterns that you might observe. So that's why you don't want to go too far back in time, but you do want to get multiple years of data. At least 3 is recommended by the Highway Safety Manual. So you average out the 3 years to get a semblance of, okay, what should be my expected crashes at this location. But if you were to plot these, so this is where I'm trying to explain the idea of the regression to the mean bias, because that was one of the questions in the quiz that most of you got right. And I think all of you got right, because The regression to the mean bias comes from the fact that crashes are random events, and their long-term average, the number each year would vary along their long-term average. Okay? So what would happen is that the long-term average would be a number that we hope would represent the expected safety of that location. However, if you were to look at like 1 year worth of data or 2 years worth of data or 3 years worth of data, you might not be at a place of the long-term average. You might get to a point where it's a little bit higher or a little bit lower than your long-term average. But guess what? If you're looking at 3 years worth of data and you are an agency, and even if you are, let's say, a statistically literate person, and you knew that there is something called a regression to the mean bias, but if you were selecting locations for the countermeasures, for implementing certain safety countermeasures, would you choose location where the 3-year average is higher than long-term average, or would you choose locations where the safety in the recent 3 years is lower than 3-year average? Right? Typically, which location would you choose? Which location would you select for improvement? Where the number of crashes is higher or lower? Right? That should be an easy question to answer. I'm looking for some answers either in the chat or via, yes. So you would be going after the location that have had higher crashes. And that would be the right strategy. Yes, I'm not saying that. So you want to look at implementing intervention where crashes have been higher. And that's the right strategy, no problem there. However, there is a little bit of a problem with that, because if you go with locations that have had higher crash counts, when you go about, when let's say you make the implementation happen, and once the implementation happens, you then try to, after the intervention, you try to assess actually if the countermeasure worked or not. Because of the regression to the mean bias, you will end up overestimating of how your countermeasure actually did. Because remember, you chose a location that was experiencing higher crash count at the time. And we know that over a longer period, the crashes would go ahead and regress to their long-term average, even if you didn't do anything, or go even lower than that over time. So if you look at the 3 years after intervention data, you will tend to overestimate your effect of your improvement. And that would happen because of the regression to the mean bias, that because crashes are random events, sometimes they will regress to their lower average without any intervention at all. But you would have no way of knowing that, because you already chose locations that were experiencing higher crashes, which was the right thing to do. But it would lead to some problems with regards to when you go about estimating the benefits of a particular countermeasure. So my question to you now is that if somebody were to come to you and ask you the why of this question. So okay, I'm gonna show you something here. So this is the EB quiz that you're looking at. And then this is the one question that everybody got right. An agency chose locations for countermeasure implementation based on the recently observed high crash counts. The agency then went on to compare the number of crashes at those locations before and after the countermeasure implementation to estimate the safety improvement or safety effect of that countermeasure. The safety improvement estimates for this location may be affected by the regression to the mean bias, right? So the answer obviously is yes, it's true. They will be affected. But now what I'm asking you is, if somebody were to follow up this true-false statement and you answer true, and somebody asked you how so, do you feel comfortable in describing how so? Do you feel comfortable in answering the question how so for this true or false statement? If you are comfortable, please raise your hand. If you're not comfortable, don't raise your hand. So I want you to raise your hand if you feel comfortable. If somebody were to follow this true false statement with a follow-up question of how so, how would that be affected by regression to the mean bias? Do you feel comfortable in being able to explain that? Raise your hand virtually if you can. Okay. So I see one hand raised, which is good. Two. Okay, good. That's good. Let me make this full screen here. Okay, 4. 5. Okay, this is not. I'm hoping for more students. So let's do this. So 6 students. Okay, that's good. Emma, if you don't mind me putting you on the spot, could you actually go ahead and answer that for me? Like, okay, how would the regression to the mean bias affect? So maybe because I did try to explain that, maybe let's hear from Emma and maybe have a little explanation showdown on who explained it better. Okay, was it Emma or was it me? But go ahead, Emma. So I don't mean to put you on the spot, but I am doing that. But why don't you go ahead and try to explain how regression to the mean bias actually affects this?
Yeah, okay. Give me 1 second.
Okay, take your time.
So how I see it is like, because they compared the number of crashes at the location that they already observed has a high crash count, there is a bias. And so the regression to mean bias, there's like an inflation there because there's like, sorry, I don't have the words in my head about it, but like, I feel like okay. I could, yeah. So like basically because they chose a location that they already observed has a high crash count, it's going to be like the bias is already there and it's going to be affected. It's not just like a random location.
Yes. So exactly. So that's another thing, right? Because we have to do observational stuff in traffic safety, we cannot randomly select locations for improvement. Right? We have to have some basis. And as Brian surely knows, when you're working for an agency, you cannot just randomly make improvements. You have to have a basis for improvement. So you're going to typically select locations with high crash counts for improvement. And I'm not against that. Like, obviously, that's the right thing to do. You want to improve safety. But the problem is, because crashes are random events, and because their distribution over long term regresses to their long term average, if you select locations that have had high crash counts, they would go down almost by default over time, right? So it's very important for agencies then to tease out what improvement is based on just regression to the mean and what improvement is based on their actual intervention, because that can help improve decision making going forward. Okay, so that's your reason, because the crashes could go down or up. Like if you start with low crash location, they could go up. But if you start with high crash location, their numbers, the crash numbers, would go down, because crashes tend to revert to their long-term average over time. So that makes it difficult for you to assess the impact of your intervention just by doing what we call the naive comparison. So the comparison that I'm describing in this true and false statement that I had for your quiz, that is a naive comparison. And if you just do a naive comparison, you are almost always going to run into that regression to the mean bias that would lead you to overestimate the impact of your improvement. Okay. So let's see, now that I and Emma have tried, how many of you feel like you could raise your hand and explain a follow-up how so question to this true false? Okay, that's good. That's very good. I'm seeing more hands raised. That's good. Okay, so now I'm going to try to put folks on the spot who have not yet raised their hands. So what I'm looking for then from you guys, maybe if you have not raised your hands. So I'm now looking at folks who haven't yet raised your hand. So I'll be looking for, no, go ahead and raise your hands. If you can answer the question, that's great. So I need to still know if you can answer that follow-up how so question. Okay, so please keep your hands raised because it's virtual, it's easy to do, right? So you can leave it raised. If you can, in fact, answer that how so question, please. Leave your hand raised if you can answer that how so question like Emma did. If you're clear on how the regression to the mean bias comes into play here in this true and false statement, please keep your hand raised. So let me now look at some folks who haven't yet raised their hands. So that means I'm assuming you're not able to explain this. So I'm going to pick on one student here, Spencer. If you're listening, Spencer, could you ask a question? What's not clear about the idea of the regression to the mean bias and how that comes into play? So I'm looking now from folks who are not able to explain that how so question to me or to the class.
Can you repeat your
question?
Can you repeat your question? The how so?
Yeah, right. So my question is, in that true and false statement that you all answered correctly, yes, the regression to the mean bias affects you. I hope you're seeing my screen as well. So for following that statement, you answered yes because you took the quiz, and maybe this question didn't show up for you, but all 16 people who did get this question, they answered correctly. So my question is, if somebody were to follow up this true false statement, which you answered as true, and they said how so, you feel comfortable in asking that or explaining that how is that the case? How does the regression to the mean bias impacts that safety improvement impact? So if you don't feel comfortable answering that question, do you have any specific question for me about that? Because I'm trying to figure out, okay, if you're not able to explain, what is the hang up here? Can you form your doubt or your sort of not being able to explain the reason for this in the form of a specific question is my thing. And this, Spencer, you're welcome to take a first crack at this.
I think I'm still trying to understand the regression to the mean bias part.
Okay, regression to the mean bias part. Okay, so I'm happy to try to explain that. Any of the other folks who don't have their hand raised, could you ask me another question? Obviously, I'm going to try to explain the regression to the mean bias real quick. Are there other folks who are not clear but can articulate their doubt in the form of a question? Please do so. That will really help me out in how I formulate my response. And I will explain the regression to the mean bias. But is there any other question that can stem from that, from folks who don't have their hands raised? Okay, so I'm going to try to explain the regression to the mean bias. So regression to the mean bias is that because crashes are random events, the numbers go up and down every time. So if for a few years, if the numbers remain high, you can almost be certain that they will go down in at least by some measure, just by themselves. Even if the agency made no improvements, even if there were no changes at all to the system, the number go up and down. And if the numbers have been high, especially high for 1 year or 2 year, and the bias will be more pronounced if you only use 1 year worth of data. If you rely on like 1 year worth of high crash counts, then the number would go down almost a certainty the next year. So, but 3 years sort of minimizes that. But even there, if you expect 3 years worth of high crash counts, the number, you could expect the number to go down by itself. So that's what we call regression to the long-term mean, or regression to the mean, RTM, is that the numbers goes down to its long-term average if the number had been high for a few years. That is especially true if you make decision based on only 1 year worth of data, but the problem is still there with 3 years worth of data. So as an agency, you don't want to make decisions based on just 1 year worth of data, because if the 1 year high crash count would almost certainly go down on its own. But if that trend has been persistent for 3 years, then that's, then that could even be going down also by its own, maybe by not all that much. And this is not to say that you don't make improvements at those sites. You do, you absolutely do. But when it comes time to assessing the effectiveness of those improvements, you be careful and apply some statistically sound methodology rather than just relying on a naive comparison of before and after crash counts. So the regression to the mean bias is the fluctuation in number that happens on its own and how that kind of progresses towards its long-term average over time. So if it has been especially high for a few years, you can expect to be especially low for the next few years. And then you would think that this is because of your intervention, if you made the intervention in the meantime, but that might just be the regression of the mean bias happening. So does that explain it, Spencer?
Yeah.
Okay, good. So for the remaining folks, could you raise your hand and let me know if all is clear? Okay. If it's still not clear, what I'll expect that, so one of the two things could be happening. So one thing could be that maybe you're not here, and that's okay. But if you're still here, why don't you reach out to me during office hours and we can talk about that. Okay. So thank you for indulging me here and just making sure that this is a very important concept, not just from a safety perspective. It is important from a safety perspective, but also from a decision-making perspective. So this is a very, very important idea that I want to make sure that everybody understands on this. And this is the whole motivation towards doing the empirical Bayes method or empirical Bayes approach, because that's what we'll try to do, is that, okay, we know this bias exists. How do we overcome this bias? How do we overcome this bias? And we overcome this bias by making a statistically sound estimate of the counterfactual. We don't compare what was happening before with what is happening after. We instead compare what would have happened before, and I'm going to call that the counterfactual. So we try to, the empirical Bayes method is there for us to be able to estimate the counterfactual. Counterfactual is what would have happened had you not applied the intervention. What would be expected to happen had you not applied the intervention? And once I estimate that counterfactual, I'm going to compare that counterfactual to what actually happened post-intervention. Okay, so let's go back to our lecture slide. And try to estimate.
I have a question about the bias. In CE421, we were using the crash modification factors on the CMF clearinghouse, and I was wondering, do you think it's safe to say that those numbers are high because they were likely used in an area with high crashes and have this bias? Or is there something in place to like ensure that those numbers aren't super biased and are like providing too high of crash modification factors?
I love that question, Megan. Thank you for asking that question. It's a so this is a great question, and I will take this on because this is sort of relevant right now, because some of you might have looked at crash modification factors in CE 421. You might have seen it in, I do talk a little bit about that when I teach the transportation economics analysis class. So the crash modification factors are basically an estimate of the improvement that you would expect following an intervention. So Megan's question is, do those crash modification factors account for that piece, right? And that crash modification factors come from the clearinghouse. So let's see. So I'm going to hide the floating routing controls, and I'm going to go to the CMF clearinghouse just a second. Okay, so the question is, the CMF factors that are provided in the crash modification factor clearinghouse that's provided by the Federal Highway Administration, and you're going to use that for this class. If you, let's say, I want to find out a crash modification factor for roundabouts, right? When I do that, hopefully my internet connection works. So category intersection design. So you could see convert to roundabout interchanges. So let's see. So this is not good, but let's kind of get to, I want to get to the intersection geometry one. Low speed roundabout. This is the crash reduction factor, CMF. So let's look at this CMF, right? So this CMF is 0.473. So basically what is this telling you is that crash modification factor is 0.473 for converting an intersection into a low speed roundabout. Crash modification factor is 4.473. And so that means if you were expecting 100 crashes before, you will only expect about 47 crashes after. So that's a very, very effective treatment. So every treatment comes with what we call a star rating. So it's a 4-star rated. And that basically will tell you whether it's a reliable rating or not. So, and that's based on study design, sample sizes, and all of that. So one of the criteria that they use based to assign the star rating is if it's a statistically rigorous design with reference group or randomized experimental and control, right? So if you're using empirical Bayes method, that's what we call the quasi-experimental design approach. So if you're using empirical Bayes design method that is accounting for all those types of biases, those CMFs would be higher rated. And in your rating kind of accounts for more factors. It accounts for study design, sample size, standard error, potential bias, all that. But if you look for studies that are like 4 rated or higher, you can expect that those studies actually do account for regression to the mean bias. So you want to look for highly rated CMFs from the crash countermeasure. So it's not to say that there are no naive comparison-based CMFs out there on that CMF clearinghouse, but you would expect them to have a lower star rating on the portal. Does that answer your question, Megan? So the short answer is look for the star rating. If the star rating is good, you can be sure that they do account for these biases. But if the star rating is low, sometimes they might be based on just naive comparison. And then you have to be very careful about applying them.
Okay, thank you.
Okay, perfect. And then one more thing about the star rating, since we are on that subject, I recently learned through my TRB interactions that, and that's the virtue of attending these types of meetings, is that if you look at that portal, the CMF Clearinghouse portal, the homepage there, upcoming webinars. So the CMF Clearinghouse will transition to a new CMF rating criteria. So they are updating the CMF rating criteria to be a little bit better than it used to be. And they're going to talk about all of those things. And there is a webinar coming up on how they are updating that rating criteria. But I still expect that rating criteria to still be, it's becoming more rigorous, even better. So I expect, the star rating to become even more reliable in the near future. So yeah, so definitely, if you're not sure if your CMF accounts for anything, look for the star rating. If the star rating is 4 or higher, you can be very comfortable. If it's 2 or lower, then then I would be very cautious about using it. If it's 3, then it's your judgment call, right? So you will review the study, and then you will decide how comfortable you feel applying that study, because they may or may not account for some things. So you'll have to kind of be a little bit judgment. You'll have to exercise your judgment in that case. Okay. So thank you for that question, Megan. That was an excellent question. And I love when folks bring up questions that some things that they have learned in other classes and try to bring those questions. So this is, again, sort of a standing invitation to bring out topics that you may have learned in other classes. And there is something that you see that's related, or maybe even like, some things that, especially if it's like a little bit contradicting even. So please feel free to raise your hand and ask questions and so on and so forth. So please go ahead and do that. And I did get a message on the chat. So let me go ahead and talk about that question as well. So I'm going to go ahead and go to my chat here. So in the chat box, I see a question. Expand on the example in the reading about the 3 Detroit intersections. So let's go ahead and look at that reading and go to that. So let's do this. Let's go back to that Detroit example once you've kind of gone through some more of the slides, and then I'll talk about those 3 Detroit intersection examples. Okay. So we'll do that in just a minute. So thank you for your question about the Detroit intersections. I'll come back to those questions that are in my chat in a little bit. Okay. Once I've done a little bit more of the. So this is the slide that explains it a little bit more even. So look for that. So the 3-year before average is represented by this blue line. You made the improvement and hopefully brought down the long-term average following that improvement to the new purple line in the after period. So 2003 was the period when the intervention was implemented. Okay, so you can see that 2003 was that period, and 2003 was the period when the implementation was implemented, the countermeasure was implemented, and hopefully that did bring down the long-term average to the new purple line in the post-2003 period. But if you were doing just a naive comparison, your observed safety impact would be affected by the red arrow, red double-headed arrow that's represented by. So you would think this is the improvement you made. But the true safety impact might be actually be represented by this green arrow. So again, that's the overestimation of improvements effectiveness that you will see if you are just relying on your own site's crash history. Okay, and that was another question, right? So if you only use your own site's crash history for traffic safety improvements effectiveness estimation, this is the bias you run into. So you don't want to rely on just on your own site. Now you might say, hey, maybe I can just go to 10 years, right? And then I will be able to estimate the purple line, the original purple line. And then I will be able to estimate a true estimate. Yes, you could do that. But the problem with going too far back into the past is that there might be so many confounding factors that might come into play. So you don't want to go too far back. So this is the beauty of the empirical Bayes analysis that you're going to learn just now, is that you can combine this 3 years worth of history from your site that is not affected by too many confounders, but still allows you to get rid of the regression to the mean bias. So how does that magic happen? How does that magic happen is you bring in more evidence from other places. Okay, so we'll talk about that in just a minute. So I hope this slide made it even clearer for that how so question that I was talking to you earlier about. Okay, So high crash locations are chosen for one reason. That might be truly high or might just be random variation. Even with no treatment, we would expect on average for this high crash frequency to decrease. This needs to be accounted for somehow. Okay, so let's see how we do that using the empirical Bayes approach. And so again, the regression to the mean bias. And then now, this is the second problem I'm talking about, and there was one question related to this in the quiz as well. So the next thing I'm talking about here is the imprecision problem. So the imprecision problem is, let's say you had 100 crashes per year at a location, and hopefully that location is not just one intersection, maybe it's a large segment of your roadway. And let's assume that the crashes are Poisson's distributed, and Poisson's is basically a statistical distribution of crash events. And let's say you had 100 crashes, and just take it from me that the estimate of the standard error can be estimated by your number of crashes per year divided by the sample size of 3 years, because you're using 3 years worth of data. And you're trying to find the standard error. So standard error could be estimated using the average divided by 3, okay, and the square root of that. Okay, so if you want to estimate what is the standard error of your 100 crashes per year estimate, you can get that standard error estimate by doing 100 divided by 3 and taking the square root of that. So you get about plus or minus 5.7 crashes per year. Or no, yeah, so your standard error would be plus or minus 5.7 crashes per year. So you could, okay, if you go one standard away from that, you will be okay. You can expect maybe about 105 crashes, or something about like 94 crashes per year. And that's your, you can go one standard deviation. If you go 2 standard deviation away, you can create like 90% confidence interval or 95% confidence interval around the average, right? But let's say now you're talking about a site that only had 1 crash per year, per 3 years. It's a site, it's a small intersection in a rural area. In 3 years' time, it has only seen 1 crash, right? Now, what I want you to do is like maybe get the calculator out. What do you think is going to be the standard error? How many crashes plus or minus per year would be the standard error? Could you do that for me using the calculation that you see for 100 crashes per year? Could you do the same calculation for me if the total crash count was like 1, 0, and 0 over a 3-year period? Could you do that for me? You take your calculators out or do it on the computer, whatever. What is, and type up in the chat box, how many crashes plus or minus would be the standard error of this 1 crash per year estimate? Let's take a minute to do that. How many crashes plus or minus is the standard error for this 1 crash per year estimate? And then also, once you figured that out, what percentage of the average is it? So let's take next couple of minutes to work this out. If you have any questions, please let me know. But what I'm trying to ask you is that basically figure out the standard error like I did for 100 crashes per year. 100 divided by 3, because that's 100 crashes per year with 3 years worth of data. So I got 100 divided by 3 and took the square root of that to get the plus or minus 5.7. And I got 5.7% of the average. I want you to do the same thing, but now your location only has 1 crash every 3 years. So I want you to apply the same formula to estimate the standard error, and then what percentage of mean is the standard error. So let's take a couple of minutes to solve this problem. And then if you get done, let's take also a 5-minute break because my watch is reminding me to walk around a little bit. So let's go ahead and do that. So let's go and take a 5-minute break and also solve this problem. So maybe let's reconvene at about, I'm going to pause the recording here. I'm going to leave the share on, but I'm going to pause the recording. Share. I hope you can still see my slide. So just want to clarify. So if you had 100 crashes per year and 3 years worth of data, you can get the standard deviation by doing 100 divided by 3 and then taking the square root of the whole thing. You get 5.7, and that's 5.7% of the average. And then if you had only 1 crash per year, so this is 1 crash per year, so total 3 crashes over 3 years, and they might be distributed differently, like 3 crashes all in 1 year, or it could be 2 crashes in 1 year and 1 crash in another year and 0 crashes in the third year or whatever. But total 1 crash per year and 3 years worth of data, the standard error would be 1 divided by 3, so that's 0.33, and you take the square root of that, and that gets you to 0.57 or so, and that would actually be almost 58% of the mean. Okay, that gets you to about 58% of the average. And that 58% is really too high. And that's the second problem. So regression to the mean was one problem. And with having very small sample sizes that lead to such large amount of error relative to the mean is another problem. And obviously, you want locations with fewer crashes. Fewer crashes are good. But when you have fewer crashes, you run into this problem of imprecision. I'm sorry, did I just get disconnected completely?
Yeah, you're no longer sharing.
Oops. So could you guys remind me what you heard last? I did talk about, did we get to this point where I mentioned 58% of the average would be the error?
Yeah, so the last thing I remember was you talking about how fewer points could pose a problem as well.
Right. So fewer points, obviously we want fewer crashes, but when you have fewer crashes, they lead to this problem of very large standard errors relative to the mean. And as in the case of one example where you had 1 crash per year with 3 years worth of data, your standard error would be about 58% of the mean. Okay. So now, how do we address that? So we saw 2 problems, regression to the mean and the imprecision problem. How does the empirical Bayes method address that? How it does it, and this is the things change idea, that you cannot go too far back by number. So if you go too far back, that could potentially help, right? Because now what you do is, like, if you go 10 years back and your average is now based on 10 years worth of data, then you increase the denominator in this. So the 3 will become 10, and that will reduce the standard error, right? So one way of trying to correct that issue is you gather more and more worth of data. But then we've talked about this, right? Things change. The conditions may not be identical to the past. The traffic volumes would change. The past trends that help forecast traffic volume, they might change as well. So going into the past may help a little bit with the standard error, but that will still be problematic in that, because there are so many confounding factors that affect safety. So you could try to address the imprecision problem by increasing the number in the denominator to 10 or 8 or something. But again, that comes with its own problem. Okay. So one way of looking at it is that, okay, one idea to address how things might change is that you might have, you might account for it by looking at, okay, you know, the average annual daily traffic would change, it will go up. Maybe I could just use rate, crash rate, by like what we learned from in our previous lectures is that, okay, we can normalize it by vehicle mile travel. Or we can normalize it if it's an intersection or whatever, we can normalize it by average annual daily traffic. The problem is the relationship between number of crashes and AADT is not completely linear in nature. So this is sort of like, you know, if you just use your rate method, you would expect the number to sort of go up in that broken line fashion. The crash frequency as a function of ADT would just go up. If that were to be the case, you could use the crash rate and not worry about AADT increases. The problem is the crash rate relationship between AADT and number of crashes might be represented by the blue line in the before scenario and with the purple line in the after scenario. And that's just a hypothetical thing, but that's the problem. That before the intervention, you might have a different nonlinear relationship between average daily traffic and crashes, and then dividing by ADT would not work. And then even making matter even worse is that you might actually end up with even different relationship post-intervention, and that could cause problems as well. So what these points are showing you is the expected value in the first scenario, expected value in the second scenario. R1 is sort of the rate, if you just were to rely on rate. So these dots, F1, F2, and F3 are different estimates that you will end up with if you were to rely on these different relationships. If you're just relying on simple rate, you will end up with F1 being your estimate of crashes in the after period. If you were to rely, like if you were to actually find the relationship from the before period, then it will end up with F2 as your expected crashes. But if you rely on the correct relationship, then you should have landed at F3. So again, you don't have to worry about this graph too much at this point, unless we talk about, and we'll discuss this in way more details in later lectures, when we actually try to build the safety performance functions. All I'm trying to tell you here with this is that you cannot just take care of this problem of AADT increase by simply accounting for rate, by normalizing by vehicle mile traveled or by normalizing by VMT, because the relationship between crashes and ADT is not linear and is subject to change over time as well. Okay, so not that it's not linear, it's not only it's not linear, it could be some curved linear relationship, but even when it's curved linear, it could actually change over time, and it could change even because of the intervention too. So a lot of issues with that. So that's why, so what I'm trying to get to this point is that I'm trying to describe various issues that you will run into that are not simply taken care of by just doing any kind of naive comparison, even if you account for the rates. So naive comparisons are not going to be helpful. Relying on evidence from just your own site, even if you account for the ADT, might not be super helpful. So what actually does help? What helps is the empirical Bayes approach. What helps is the empirical Bayes approach here. So let's see, why am I not seeing that? Are you guys still here? Everybody still able to listen to me? Maybe give me a thumbs up. Okay, perfect. Okay, so what I'm trying to do now is I'm trying to get, okay, perfect. I'm trying to do, go ahead and stop sharing real quick and restart the sharing. And this time share my, I know I stopped sharing for a second here. So I'm going to go ahead and share my, so now I've given you regression to the mean. I've given you the non-linear relationship between ADT and crashes, and I've given you the imprecision problem. So I've given you 3 different problems that are responsible or that basically cause for you to not just look at your own site of interest where you're trying to implement improvement. You cannot just look at that site. For those three reasons, you cannot just look at those three sites to make decision on safety improvements effectiveness. What you need to do then is you need to bring in more evidence now. An empirical Bayes method allows us to combine two different sets of evidences. What are those two sets of evidences? Those two sets come from one, from your own site. We've talked about how it's not reliable on its own, but that doesn't mean it's completely useless. The crash history of your site is useful, even though it's not sufficient by itself. So you combine that, you combine your site's history with some cross-sectional evidence. Okay? So what do I mean by cross-sectional evidence? Cross-sectional evidence is that you combine information, you bring in information from sites that are similar to your site. And then on those sites, you estimate a cross-sectional regression model. Okay? That defines what we call the safety performance function. Is that how is a typical, let's say your site of interest is two-way stop control intersection, is that with those cross-sectional evidence, what you're trying to bring in is that how does a two-way stop control intersection is supposed to behave? Given its ADT, how many crashes are expected? And for that, you collect data from what we call the reference sites. Okay, there are sites that are similar to your site of interest, but they are different from your site of interest. So they are similar, but they are different. They are similar, but are located at different locations. So different locations that are similar to your site of interest, you have a regression model that defines the regression model defines the crash frequency on the left-hand side with a bunch of explanatory variables. So you can plug in your site's information to get an expected value based on that model. So what are the two evidences? One evidence is the site history, the crash history of your own site. And the second evidence is the cross-section model that defines the relationship between number of crashes and the characteristics of a site. Okay. So, and when you combine those two sets of evidences, these two combined give you the counterfactual. So let's see if I have that. So instead of going through all these sites, because I need to need to wrap this lecture up in just a second, I wanna stop share for a second. I want you to mull over these sites, this approach, and the problems that we talked about. And I want to share like a very important figure here. I'm gonna go ahead and stop share. And I want to share go ahead and stop. So I want to give you another minute to sort of mull over what we just talked about. And in the meantime, I want to share a figure with you that I think is very important. And I'll add that to the slide here. If you have any questions in the meantime, please feel free to type them up in the chat box. So I want to add this figure. Oops. So add this image here. So I'm going to bring in this image here. Okay. So first of all, are there any questions about what we've been talking about? Anything that still sort of is lingering about regression to the mean bias, about the imprecision problem, about the fact why just merely converting in everything from crash counts to crash rate, which is normalized by ADT, is not sufficient. And then all of that to combine is that the data from your own site where you're trying to implement intervention is not enough, and how you need to bring in some cross-sectional evidence. So is that rationale clear of trying to bring in the cross-sectional evidence or evidence from sites that are similar? And I haven't yet discussed how that will help with all these three different problems that I've discussed, but we do know that the site history by itself won't be sufficient. So are there any questions about that? So I know some hands are already raised, but I think they might have been raised for a previous question that I had asked. So go ahead and lower your hands if you had raised them for previous question. But are there any questions about why data from your own site of intervention is not sufficient? Okay, Emma and Will, do you have questions about this, or your hand raised based on a previous prompt of mine? Okay. So any questions so far about why data from your own site may not be sufficient? Okay. So what I did do in the meantime, go ahead and start sharing my screen again. I created the empirical Bayes framework. I said that the safety estimate based on the history of the site before treatment by itself is not enough. But as I said, it's not useless either. So I want to use this. And then safety estimate based on other similar sites. And this is where what comes from safety performance functions. And typically, these safety performance functions would be some negative binomial regression model, okay, where you can plug in the characteristics of your site and get an estimate of how many crashes were you expecting. And where does that regression model come from? That regression model comes from sites that are similar to your sites, but somebody else has already analyzed their crash data, their geometric design data, their ADT data, and combined them in the form of a regression model. And these safety performance functions are what you find in the highway safety manual. So you plug in the characteristics of your site's ADT, and any geometric design characteristics and whatever is needed from the safety performance functions. And you plug that in, and you will get a number of how many crashes should you expect on your site. Okay. And then you will also get a number like 3 years average from your site. So that will be this piece. And then you combine them using some weighted average. Okay. And we'll learn how to get this weighted average. And then once you combine the two using a weighted average, combine these two sets of evidences using a weighted average, then that gives you the counterfactual safety estimate without the treatment. That means that gives you what would have happened had you not applied the safety treatment. And then you can compare it to once you apply the intervention, and then you observe 1 year, 2 year, 3 years worth of crash history in the post-treatment period. Then you can compare B with A. B is your counterfactual. A is the actual safety of what really happened on the site after your intervention. And then you can use B and A to estimate what is the actual safety improvement because of your intervention. Now, I have a quick question for you. Let's say you did all this process, and we are going to learn to do just that in the coming lecture on Tuesday, 1 week from today. We'll learn to do just this. How do we estimate this B? The counterfactual safety estimate without the treatment, with some data that's sort of made up in the tutorial, but then also we'll use it from some real world data in a lab exercise later on as well. So we'll learn to do all of that. So we'll make use of some spreadsheets and so forth. But for now, my sort of question that I want you to think about as we try to wrap this up today's lecture. Let's say if you had the estimate for B, you did all this process and you got the estimate for B. And then you also collected data post-intervention for A. So you had the crash counts post-intervention, the number A. And then you had the counterfactual estimate using all of this analysis using empirical Bayes method B. Could you represent, in the chat box, please answer the question. Could you represent, and I'll maybe type this question up too. Could you represent the crash modification factor? Could you represent crash modification factor? You represents crash modification factor in terms of B and A. Can you write a quick formula from what you know about the crash modification factor in terms of B and A? And it's okay if you can't answer that question because you haven't heard of crash modification factor in any of your other classes, because I don't expect all of you to have taken CE 421 or CE 528. So it's possible that you haven't heard of CMF, but we did mention that in earlier class earlier today. So maybe you got some idea from there. But could you represent CMF in terms of B versus A? And B and A, B being the counterfactual crash estimate, what would have happened without the intervention, safety intervention, and A is actually what did happen after the intervention. So if you were to estimate, yeah, A over B. Yeah, that's correct. So the ratio, so what I'm hearing from students is that the ratio of B and A gives you the crash modification factor. That's exactly right. So if you get the counterfactual estimate, A divided by B is your CMF. That's exactly right. So A divided by B equal to CMF. Now, obviously, empirical Bayes approach is just there for you to help estimate B. Because A is trivial, right? A is just, you just have to go out and count the number of crashes that happened in the after period. So A is pretty easy to get in the slide there, but B is where most of the action is. And in the next class, we'll learn to estimate B using our Ezra Howard's tutorial that I posted. And so we'll pick that discussion up in the next class on Tuesday. Our Thursday's lesson would be about working on the lab assignment, and hopefully we'll have our student assistant with us who can help us out with the coding and stuff. So Thursday's lab will devote wholly to the lab exercise that you're working with. So come prepared with your lab coding questions, and we'll pick up the discussion on crash modification factor and the estimate of the counterfactual using the empirical Bayes method on Tuesday's lecture, 1 week from today. So unless there are some questions, some burning questions you want to ask me, I will go ahead and stop the lecture. Feel free to raise your hand or type your question in the chat box if you have any questions. I'm not seeing any raised hand or questions, so I'm going to go ahead and stop recording.